Everybody dance. Okay, we will call to order the Oak Island Town Council Special Meeting of May 13th, 2014. The purpose of this meeting is to allow council to get presentations and be able to ask questions of a representative from Black and Beach, who were the engineers of our wastewater system, and also from AirVac, who are the manufacturers of the equipment that we use in our vacuum stations, our vacuum operations, our valve pits, and so forth. We will have presentations first by Black and Beach, and then presentation by AirVac, and then we will open up the floor to council and let them ask any questions that they need to ask. Part of this came out of the discussions from council recently about the capacities of our system in the different areas in relation to the larger homes and just also just regular areas of full capacity on what we can do in the different sections. How do we need a plan for the future? This is not a meeting to go over why we did it, how much it costs, all those questions that have been asked before. We had a town hall meeting in November of 2011, and that was, we had a presentation by AirVac, we had a presentation by Black and Beach. Matt, I think you were here for that one with Alan Reimer. And I think Clint from AirVac was our representative then. We have DVD copies of that particular town hall meeting, and most of the questions that I've been asked from everybody were answered at that meeting. If you would like to get a DVD copy of that meeting, all you have to do is let us know, and we'll make sure that Kyle gets you a copy, and I'll ask that the manager not charge you anything for those copies of those DVDs because it is such an important subject. So to begin, Matt, if you won't mind, come and give us your presentation on how our system was designed. And I think and council, correct me if I'm wrong, I think we are very much interested in more than how it was designed, but how it was installed. What was the final installation of our system? Kind of an overview.
Again, thank you, Madam Mayor, for the introduction. We were asked to come here and basically give a presentation on how the design considerations that went into sizing the collection system and basically the layout of the system, including the pipelines and the vacuum stations and the main lift station, which conveys wastewater off the island. How do I get the... there we go. My presentation today, I was going to touch on three items mainly. I'll give a presentation on, or I'll give a overview of the populations. The population basis was how we sized the collection system, the number of people on the island, and the wastewater generated by each person. I'll also talk briefly on peaking factors. That's an important consideration when you size the system because whereas a person might generate, say, 100 gallons of wastewater a day, most of that wastewater is generated in the morning and the evening as they're getting ready to go to work and then getting ready for bed. So you have to size your system to accommodate that peak flow. And finally, I'll give a brief overview on the vacuum collection system as well as the Middleton lift station. The first item, the population. There are basically two populations within Oak Island. There's a permanent population that lives year-round, and there's also a seasonal population that can vary. Obviously, you have more people here in the summer that are coming here for vacation. The permanent population data, that was taken from the 2000 U.S. Census. Based on that census, we came up with an average household size of 2.14 people per lot. To get the wastewater flows, we analyzed existing historical average wastewater flow data from the Yopon Beach gravity sewer system. At the time when we designed the vacuum system, that was the closest and best available data source to look at. Based on that historical data, we saw that we get about 85 gallons per person per day. Likewise, we did a similar analysis of seasonal populations. Again, we looked at the 2000 U.S. Census, as well as the Consolidated Oak Island Land Use Plan, which I believe is the submittal that's required to the state, as well as we looked at the Environmental Impact Statement and the Land Use and Development Plan that was done as part of the Second Bridge to Oak Island project. That was a DOT project out on Middleton Drive. Analysis of that data showed that the seasonal population is approximately 3.2 times the permanent population. That's on an average yearly basis. Obviously, it's a little bit higher than 3.2, probably July 4th week. It's probably a little bit lower than that in the middle of the winter. Multiplying that permanent population by 3.2 gives us a seasonal population of 6.85 people per lot. Again, we looked at the historical wastewater flows from the Yopon Beach system, and based on that, we came up with a per capita flow of 50 gallons per day seasonal population. Kind of makes sense if you think about it. Someone on vacation is probably not going to use as much water as someone who lives here year-round. Again, it's an average. I'm sure there are some people on vacation that use a lot of water. So that's a summary of the seasonal and permanent population projections. From those population projections, we looked at an average wastewater flow per residence. For purposes of design and planning, we kind of broke the island into two distinct portions. Service areas 4, 5, 6, 7, 8, and 9, which if you've looked at the maps that AirVac brought, that's the service areas that are kind of bounded by Oak Island Drive and Yacht Drive. It's not the beachfront area. Some of the houses do back up onto the ICW, as well as I believe some of them back up onto the Davis Canal. But it's really not the beachfront area. The population data we had showed that you see more of a mixture of permanent and seasonal populations in there. And based on that, I believe it was a 40% seasonal, 60% permanent was what we saw. And based on that, we get an average wastewater flow of 250 gallons per day per house, based on that ratio of 40-60. Service areas 1, 2, and 3, we termed the beachfront area. That's again, if the maps from AirVac, that's the portion of the island that's along Beach Drive and Dolphin Drive. That area tends to have a higher seasonal population, a lot of beach rental houses. And based on that, we saw they have a higher seasonal population than permanent population. So those were estimated at about an average wastewater flow of 350 gallons per day. Again, that's an average daily flow. That's a summary of the residential flows. There are also commercial flows that have to be accounted for. When doing commercial flows, there's a specific North Carolina statute that covers various flow from commercial facilities. And that's the specific statute up there, the 2T rules. For example, if you have a school, the flow is based on the number of students. Motels are based on the number of rooms, and restaurants will be based on the number of seats. There were, like I said, the commercial facilities that are within the vacuum sewer system were used. The flows from those were calculated using the 2T rules. Again, as I touched on earlier, when you size your wastewater collection system, you need to account for a peaking factor. Again, the flows I talked about earlier were an average daily flow. However, the majority of your wastewater is generated in the morning and the evening as you're getting ready for work or school or getting ready to go to bed. So you have what's called a diurnal curve. and basically you look at the ratio of the high point on the curve to the average. The state of North Carolina Department of Environment and Natural Resources recommends a peaking factor of 2.5 in their design. So that's what we used when we sized it. That basically means...
Matt, excuse me. What am I hearing in the room? Is it an echo? Pardon? Two people were talking. I couldn't figure. Okay, go ahead.
See, I think he's got a microphone back there.
He doesn't see anything.
Pardon?
He doesn't see anything that's going on right now, so.
Okay. All right. Go ahead, Matt.
Okay. So the peaking factor of 2.5 that the state recommends, what that equates to is your average daily flow, say of 250 gallons, I believe, is what we had for a permanent household. Your peak flow would be 2.5 times that. I'll give a brief overview of the collection system. AirVac will have a lot more detailed information on that, so I'll try not to bore everyone with this. But each service area consists of a vacuum station that has vacuum pumps. Each of those vacuum pumps puts a vacuum on the pipelines. Wastewater is pulled through the vacuum pipelines to a storage tank within the vacuum station. Again, there are 9 vacuum stations within the town of Oak Island. From the storage tank and the vacuum station, sewage pumps will empty the storage tank, pump the wastewater into a pressure force main network, and ultimately to the Middleton Lift Station, which is located at the intersection of East Oak Island Drive and Middleton Drive. It's co-located with Vacuum Station 5. And the Middleton Lift Station is what's used to pump all the wastewater off of the island. From the Middleton Lift Station, it's pumped to the West Brunswick Regional Water Reclamation Facility, which is on the mainland North Carolina for ultimate treatment and disposal. Again, kind of a summary of the design conditions for the vacuum collection system. The system was designed for ultimate build-out of the island, meaning that in our design, we assumed there was a house on each lot that was contributing wastewater to the system. And that design was based on the available property lot information at the time of design. Collection system pipelines were sized for, that's the max daily flow, that's that average daily flow with the peaking factor, and then converted from gallons per day to gallons per minute. We get 0.425 gallons per minute per lot from the mainland portion. Again, that's areas 4, 5, 6, 7, 8, and 9. And 0.59 GPM for the beachfront portion, which is areas 1, 2, and 3. Again, the higher number for the beachfront is because we saw a greater seasonal population in that area. And then based on the value, the wastewater flow per lot, those numbers were provided to AirVac, who then sized the storage tanks and the sewage pumps based on the total flow to each of the 9 vacuum stations. The force main network, this is what collects all the wastewater from the vacuum stations and conveys it to the Middleton Lift Station. Again, it accepts flow from all 9 vacuum stations. The force mains ultimately discharged to the Middleton Lift Station. Service areas 1, 2, and 4 feed into a single force main that connects to the west side of the Middleton Lift Station, and the remaining areas 3, 6, 7, 8, 9 feed into another force main that connects to the east side of the lift station. Service area 5 is co-located with the Middleton Lift Station and just dumps directly into the wet well of the Middleton Lift Station. The Middleton Lift Station itself consists of 3 submersible sewage pumps. Each pump is rated at 2,250 gallons per minute. Per state guidelines, you have to have 2 duty pumps and 1 standby. That way, in case you have a problem with one pump, you're not out of commission. You can still pump wastewater. The idea being that, you know, if you've got one pump out, you can work on that, but your station is still operational. The Middleton Lift Station is a 4,500 gallons per minute total permitted capacity, and that is sized to accept flow from all 9 vacuum stations. The Middleton Lift Station has an emergency backup power supply, which is a permanent on-site generator with an automatic transfer switch. So if it gets a message that the power from the local utility is out, it will automatically transfer to the generator. And there are alarms built into that, so I believe, correct me if I'm wrong, David, but you get a phone call or a text message or something that says there's a problem, go look at it. The Middleton Lift Station, again, ultimately that pumps the wastewater off the island. There's a 20-inch force main that goes down West Oak Island Drive. There's a 24-inch line that crosses underneath the intercoastal waterway. Both of those were designed by Black & Beach. Once it gets to the mainland, there are a series of 20-inch force mains that convey it to its ultimate treatment location. Those force mains were designed by other design firms, so I really can't go into detail on that. And that was the end of my show.
Generator.
Kyle, if we could turn the lights up, but would council prefer to hear from Airback and then start asking questions? Mm-hmm. Okay, I'm sorry, Kyle. I should have asked council first. Turn the lights back off again. And I neglected to say when I opened the meeting, after these presentations, we're going to open up for questions from council. If we have time, we're going to adjourn at 4 o'clock. We have our regular town council meeting at 6 this evening with a very heavy agenda. If we have time, after council questions, I have a handheld mic here, and I'll come out in the room and ask if anyone has any questions. I will moderate these questions so that they are questions about our system as it's installed and the ultimate capacities of it. So if you have questions, form them from these presentations and what your questions are about our system's capacities. I'm sorry, go ahead.
Okay, my name's Frank Bland, and I've been involved in this project since the inception, about 2001, with the town of Oak Island, and I thank you for the opportunity to come and explain our technology to all you from the public, and we'll get started. Airback's been doing wastewater collection on residential communities since 1972, and there's 3 major components to the system itself: the vacuum collection station you see there to your right, the vacuum main collection network that connects the valve pick packages in the homes to the collection system itself. This is showing some examples, some pictures of our valve pit package that you may have out in the right of way in front of your house. We have the one-piece, upper left-hand picture shows the one-piece pit. The lower right-hand picture shows our latest version of our, what we call our 2-piece pit. And up in the right-hand corner, you can see the 6-inch dedicated air terminal that you're probably familiar with out in front of your home that gives the atmospheric air to propel that sewage downline. And the other picture to the lower left is looking down into our valve pit that shows that the operators are never exposed to the raw sewage. The pit bottom keeps the collection sump from the valve chamber separated. It can fill with groundwater in the upper chamber, and that valve and controller, they're both designed to work totally submerged underwater. This is our gravity home connection slide, and we're showing the building sewer or the gravity service coming from the home to the collection sump itself, and we're showing the 4-inch air intake, or with what we have mainly here at Oak Island, or you have both versions. You have the 4-inch air intake that has to be on each individual gravity service going up to the home, or you could have the 6-inch dedicated air terminal out by the valve pit in the right-of-way that eliminates the access to your property. Once again, those air terminals and 6-inch dedicated air terminal is where it gets its atmospheric air that propels the sewage down line. Here again, we're showing the gravity home connection coming into the pit in the lower right sump. Some finished grading going on to the left. We do use pressure-rated SDR 21, 26, or Schedule 40 PVC pipe. And when the contractor goes in and installs the system initially, there's a 6-inch minimum stub out going toward the property line for your gravity services to connect to. The valve pit package itself, they're H20 traffic load rating, so they can be in a right-of-way where there is opportunity for traffic to drive over the valve pit, if that should be the case. We also are showing the service line, the 3-inch service line under vacuum coming out of that valve pit and into the vacuum main itself. Let me back up one moment. The way our system works, the vacuum station generates, they have the vacuum pumps that pull the air off of that collection tank, as well as the piping network throughout the community, creating a negative pressure within that collection tank and the piping network. And the vacuum is up to that valve in the closed position. When 10 gallons of sewage or 2 flushes get to the bottom of that collection sump, that liquid level rising compresses the air in our sensor tube, 2-inch sensor pipe that triggers the controller on the top of that valve to actuate that valve, lets the vacuum from in front of that valve be applied to the upper bonnet, pulls the plunger open. Now your sump is exposed to that negative pressure, 16 to 20 inches of mercury vacuum. So it takes that 10 gallons of liquid out of that sump at 15 to 18 feet per second. It's very violent, dissipates any of the solids to a slurry. Anything that will go through a 2 7/8 toilet throat will go through that 3-inch valve. Our 1-piece valve pit package is rotationally molded, 1-piece polyethylene construction, and it also has a buoyancy collar around the center of it. The valve pits are typically located at the common lot line at the property corner within the right-of-way, typically opposite of your water services. The valve pit packages can typically handle up to 2 homes. They are designed that they can handle 4 homes, flow capacity of 3 gallons per minute, but more frequently we see them with 2 homes. If you had a rear lot alley situation where you had 4 common lot corners coming to the same place, you can connect 4 homes to one of these, but it's more common for them to be out in the front where it's 2 homes to 1 valve pit, and then you'll have another valve pit on the opposite side of the street collecting from another 2 homes. They come in various depths for various applications, and they range from 5 feet to 7.5 feet deep. Once again, they are H20 traffic load rated. Our 2-piece valve pit, I don't know, David, do you have any of the new 2-piece down here? That collection sump and pit bottom are all rotationally molded. The upper cone is fiberglass, and we have our anti-buoyancy collar again at the middle of it, and we have a typical manhole ring and cover on top. This is showing our 3-inch valve. This is a cutaway version. There you got an idea of the velocities all by itself going through the valve. I didn't do that. I don't know how it happened. They are glass-filled polypropylene and stainless steel parts. They're chemically and corrosion-resistant construction. They have a full 3-inch port opening, so a 3-inch solid will go through. As I said, anything that goes through a 2 7/8 toilet throat will pass through our valve. You never really have to remove that Y body. We recommend every 7 to 10 years you rebuild that valve and controller. In order to do so, you just spin that upper housing out, take that back to the shop, put another one in, and you can do the rebuild at your shop on a rainy day. The controller comes off with a slip key mechanism on the top for easy removal. The controller and the valve are designed that most of the time, if there's a problem, it's going to be in that controller, and it's real easy to be removed, taken back to the shop and tested. The guy can put another one on there in just a matter of seconds and be back in operation. As I referred to, the maintenance on the 3-inch vacuum valve and controller, rebuilds for the valve every 15 years, rebuild on the controller every 10 years. Total cost is about $70. We recommend that 3% spare parts are kept on site for quick changes in the field. That's a new number on me, Denny, that 10 and 15. We were 7 to 10 for years. Here again, I've got,
Could you back up to that last slide, please?
sure.
Okay, I'm good.
Sorry, who asked a question?
No, I was just taking notes.
Okay.
We're moving too fast.
Can I ask a question so it might help them? Could you provide a copy of this for us so we can print these out for the board members?
Sure.
Okay. And that would keep you from having to write all this down.
And if you don't mind, Steve, the website and also channel 16-10 it is now, I think is, so.
Lisa, put it on the website.
Back to the previous slide, please. Frank, could you go back one more time, please?
Yes, ma'am.
And you just made a comment about the 7 to 10 year life versus what's on this
I
slide.
apologize for that. I've been doing this 23 years, and the first 10, 15 years of my career, it was 7 to 10 years. And it's
So
been
now
recently updated to 10 to 15 years.
Okay.
And I apologize for my slip. I should have read and not been letting my mouth run in front of my eyes reading. I apologize. Here we're showing the one-piece valve pit package that you have a lot of here at Holden Beach, or I'm sorry, at Oak Island. And that's all rotationally molded polyethylene. Hopefully we can get these two little video pegs over here to work. Once again, to show that velocity is going through that valve at 15 to 18 feet per second.
Wait.
Oh, goodness.
There it goes.
And down in the collection sump, you get an idea of those velocities. We've got a couple diapers laying in there. We did all this earlier. And this should kind of give you an idea how everything, if it'll go through, it'll go up that 3-inch suction pipe.
We don't recommend that you do this.
Don't try this at home.
Yeah.
All of our valve pits do have a cast iron manhole ring and cover on top. Once again, they are H20 traffic load rated, usually installed in the right of way. And if you're going to have a lot of traffic going over, we do recommend that a concrete collar be placed around that manhole ring or that ring and cover. We're showing some examples of the 4-inch air intakes, as well as the 6-inch dedicated air terminal. This eliminates the individual 4-inch air intakes on each gravity service coming from the homes. One dedicated air terminal per valve pit gives the operator accessible, makes it operator accessible in the right-of-ways versus air intakes up on the private property. They're available in different colors from simulated stone, utility green, what have you. This is showing our flex connector. That's a piece of flexible PVC that comes out of the 3-inch valve at the valve pit and connects to the Y connection of the vacuum main, eliminates the needs for a lot of rigid pipe fittings that we used in our past, eliminates a lot of glued joints. Here's some examples of the flex connector tying into the Y, into the main itself. Buffer tanks, that's how we handle higher flow users. Our valve pit will handle 3 gallons a minute peak flow. We have buffer tanks which can be either fiberglass or standard sanitary, concrete sanitary manholes with sumps formed on the interior, the bottoms of the manhole. A single buffer tank would have one air vac valve mounted on the interior wall, will handle up to 15 gallons a minute peak flow. You can put as many as 4, make a quad buffer tank that'll handle 60 gallons a minute peak flow. If you had a Holiday Inn or higher flow users, this is the way we bring them into our system. You can see on your right there the sumps formed in the bottom with the vacuum valves mounted to the interior walls. Same suction and sensor pipes, they work the same way. 10 gallons of liquid get into that sump, that valve fires and evacuates that 10 gallons in 2 to 3 seconds, followed by atmospheric air. Showing some schematics of some fiberglass buffer tanks that we're now producing. The only problem with these is they cannot be in a traffic bearing situation. Vacuum system design, I'm going to go through a little bit of the layout and the piping network. Ideally, you try to centrally locate the vacuum station. That gives us the ability to bring multiple mains into that collection station, go different directions, essentially breaking the community into various zones. With that, on each individual line, we put resilient wedge gate valves at any branch lines or 1,000, 1,500 feet on straight long runs. What this essentially does, the valves are just similar to a water system in reverse. This is for isolation purposes, should there ever be a problem within your system. I'll quickly run through how a problem could be located or a loss in our vacuum system could be located. Typically, the operations people need to go and check the vacuum station once a day. There's a circular chart recorder on the control panel in that collection station, excuse me, that monitors the runtime of the vacuum pumps. One of the other misconceptions is these vacuum pumps run 24/7. That's not the case. We run between 16 and 20 inches of mercury vacuum. So the station are sitting at 20 inches of mercury vacuum. At peak times, firing of the valves depletes that vacuum down to 16 inches. The vacuum pump comes on. They're designed to bring that vacuum level up to 20 inches in 3 minutes or less. So the vacuum pumps run in 3 to 4 minute bursts. Typically, we see total run times 4 to 6 hours a day for the vacuum pumps. It's not a 24/7 thing. So let's get back to how do we isolate if there's a problem. So the operator comes in, he sees there's more run time on those vacuum pumps on that chart recorder. On the incoming vacuum mains, for this picture, we have 3 incoming vacuum mains. As it comes into that red box, the vacuum station, as it comes into the collection tank, there are division valves right at the collection tank with vacuum gauges. So the operator, the first thing he'd do is shut down that division valve on that first incoming line. If the vacuum stays steady on the other 2 incoming lines, then he knows that the losses occurred in this quadrant of the community or on this main. Then he goes out to the midpoint of that line, to that division valve. Same thing, shut that division valve down. There's a little gauge tap there. If his gauge shows vacuum steady, then he knows the losses between there and the end of the system. So you can basically get it down to a city block. From that point on, they walk down the street, listen at the air intakes. If it's a hung valve, you'll hear it right at the air intake. If it's not a hung valve, then you're looking for, has anybody been in there with a backhoe? Has there been any surface disruption? But each valve pit along that system in that city block is an access point where you can get into that, take the manhole cover off, you can get in there and listen, you can hear you can hear the vacuum, you can hear if it's pulling air. So usually it's pretty easy to get and locate wherever the losses occurred. On our larger systems, usually 30 minutes or less, you can locate that vacuum loss and identify it and make that correction to the system. Usually if there's a break in a line, it's a shallow burial because of the smaller diameter pipe and shallow trenches. So you put a repair coupling on it, shut the division valve before and after to isolate that line, put the repair coupling on, and it should be a quick process. This is giving you an idea of, I won't get into it too much, but our 4-inch vacuum mains will handle up to 52 EDUs, 6-inch, then you bump up to 6-inch line. Our lines are sized according to flow. 6-inch line will handle 143 EDUs. You can put about 287 on an 8-inch line and 512 on a 10-inch line. So if you're looking at serving 1,500 homes, you're going to have 3 10-inch lines coming into that vacuum station. For identifying purposes here, our green represents our 4-inch line, the orange is our 6, the 8's the blue, and the 10-inch is the yellow. And you see from the green to the orange to the blue, that's accumulation of flow from the end of the line to the station. And the red numbers depict how many connections you have as you go along that line. Typical service layout, as I said, the valve pits will be located at the right-of-way. The common lot line, usually opposite corner than your water service. And 2 homes to 1 valve pit. The vacuum main is going down one side of the street or the other, and we'll have valve pits typically going down both sides of the street. Liquid level transport. Level grade, we're going to go, you can put what we call lifts in. Let's say your minimum cover is 3.5 feet. if you've gone, we do can lay our pipe at 0.2%, which is flatter than conventional gravity. But if you go 500 feet, you've now fallen a foot for demonstration purposes. You can put a lift in, which is a 45-degree bend, short piece of pipe, another 45-degree bend. Now you've recouped that foot of fall. You're back at minimum cover on your pipe, the ability to keep everything shallow in high groundwater conditions. It also gives you the ability to bob and weave vertically around any obstructions, whether it be storm pipes or culverts or anything of that nature. When we do uphill transport, you can bring those lifts together. It gives you the ability to do some uphill transport. If you've got downhill grade going toward the station, we can just go with, as long as we've got greater than 0.2% slope on the pipe. This is showing the lift down in your lower left, and what we call our sawtooth profile is the lifts. Bringing them closer together gives you the ability, as I said, to overcome some topography. This is describing that example, the 500 feet. At 0.2, you fall in a foot, or 750 feet, you fall in a foot and a half. You don't have to do that, but if you want to keep it shallow, this is how we do it. With that in mind, from the vacuum station in level conditions, we can reach out approximately 10,000 feet in any direction. The uphill transport, as I said, the flattest we can leave it is at 0.2%. And when you approach one of these lifts, the last 50 feet prior to a lift has to be laid at 0.2%. What that does is keeps the liquid from choking off that lift. When the liquid does come to left, you'll see in the dark blue at the bottom of the lifts, we design our system at 1/3 liquid, 2/3 airspace. That gives it the ability to not choke the lifts off, so the vacuum can get from your vacuum station to your furthest valve pits furthest away from the station. This is the difference in the technology evolved over the years. And it's given us the ability to reach out there between 7,500 and 10,000 feet. Downhill transport, once again, we can keep the grade of the pipe is similar to the lay of the land. There's no maximum downhill slope, but prior to any lifts, you've got to put that last 50 feet at 0.2%. This is showing an example of a vacuum main profile. The branch lines come into the main with the over-top connection. You can roll those Ys over at 45 degrees. Main things keep that flow coming in over the top. We don't want to see any more than 5 consecutive space lifts at 20 feet apart. Once you've done it, lifted it 5 times, we recommend you go 125 feet at 0.2% before you do another series of lifts. The 50 feet minimum slope at 0.2% prior to the lifts. Downhill transport, as I said, we can follow the ground. And once again, the flattest we can lay that pipe is 0.2% grade going towards your station. The system hydraulics, in a perfect vacuum of 30 inches mercury vacuum, you can lift a column of water 34 feet. We work between 16 and 20 inches of mercury vacuum, so that low end of ours is 16 inches, equates to 18 feet of water column. We know it takes about 5 inches to fire our valve, so we try not to have any more than 13 feet of calculated lift designed into our systems. That's how that all came about. This is showing losses due to lifts, and for talking purposes, we're using 6-inch pipe, and we're doing invert to invert a 1.5 foot lift. Well, if you noticed, probably didn't get a chance to notice it, but when that valve fires and that liquid's going through the line, it's actually spiraling. So it's going from the crown of that lower at the bottom of the lift to the invert at the top of the lift. So with that in mind, we're doing invert to invert 1.5 foot, but you less out that 6 inches of that pipe diameter, and that gives us a calculated loss of 1 foot in that 1.5 foot lift. Static head loss. Static head loss is due to the elevation of the part of the pipeline above its source. Properly sized systems are equal to or less than 13 feet of calculated loss. Once again, we use the air to liquid ratio of 1/3 liquid, 2/3 airspace. That gives the ability for that vacuum to get over top of that liquid all the way to the end of your system. Now, hopefully I can get these little videos to give you an idea again of this liquid level transport. Oh, goodness. There's, get you an idea of those velocities. That one's not real good. Okay, how do I get back?
Go back.
Sorry. Apologize for my technical
Number 41.
ignorance. What?
41.
Where'd I end up, Denny?
Escape.
Okay, I'm good. The air to liquid ratio, we just went through that. Now, liquid.
There you go.
There you go.
All right, I wanted to get them an idea that hopefully you can see this lift when it fires. I apologize about my technical difficulty. This is showing the lift and valve firing. You get the idea of the liquid being able to climb those lifts. All right, how do I get out of this? Anybody got an idea? Yeah, that's what
Hit
it is.
escape, yeah,
Okay,
there you
okay.
go.
Thank you. The vacuum main materials, piping materials, we use 3-inch service laterals coming out of our 3-inch vacuum valve and connecting to the main. The smallest diameter main we use is 4-inch. We use 4, 6, 8, and 10-inch vacuum mains. Once again, it's SDR21 or Schedule 40 PVC. All the pipe manufacturers require that the Reber-style gasket be used in order to be certified for use in a vacuum situation. The Reber-style gasket is a double-lip gasket. No additional cost to the pipe, but that's what's required for use in a vacuum situation. Vacuum main fittings, Schedule 40 PVC pressure-rated fittings. They have the Reber-style gaskets are preferred. We did years ago. We used all solvent-welded fittings, but now we have companies out there producing pressure-rated fittings with the Reber-style gaskets in it. We never use T's in a vacuum system, Y's only. Division valves, we use resilient wedge gate valves. Vacuum main repair. Vacuum mains are easily accessible due to shallow burial depths, making the repairs quick and easy, minimizing any system downtime, as well as minimizing any surface disruption leading to additional repair costs. Once again, shut the division valve prior to and after upstream and downstream of your break, and get in there with the repair coupling, and you should be back up and running in no time. Vacuum main installation. This is showing vacuum main on the left, gravity on the right. Once again, smaller diameter trenches and shallow depth of pipe. We do have the ability to do some aerial crossings. You can strap to the bridge if necessary, as long as you have the lift available. All of our piping that goes in the ground is supposed to be tested daily. Normally, we provide a trailer-mounted vacuum pump and a field man on the job that, at the end of the day, he's going to put at least a 2-hour daily test on the pipe that's put in the ground. And then at the end of all the construction, there's a 4-hour final test done on the entire system. So if your contractor shortchanges you on his daily testing, it usually catches him there at the end in that final testing. Doesn't pay to skimp on your testing of your installed pipe. Vacuum station design, I'm just going to go through some examples of different vacuum station scenarios. Typical station configuration, collection tank in the bottom with the sewage pumps, electrical panel and the vacuum pumps up at the higher level, usually out of the floodplain. This was a one-story, all on one level station. Typical vacuum station configurations, 2 to 3 vacuum pumps, 2 sewage pumps and collection tanks. I don't know how all the components are sized. We use Bush rotary vane vacuum pumps. They're designed on total peak flow, the total system pipe volume, and the air to liquid ratio, and that system pump downtime. Collection tank sizing. The volume of the collection tank is 3 times the operating volume plus an extra 400 gallons volume so that it helps us with the buffer volume so that those vacuum pumps don't see initial firings out there. These are based on two factors. One, prevent excessive discharge pumping cycles, as I referred to, and to provide emergency storage if it's necessary. Some small stations, number of connections, 100 to 300, typically 2 vacuum pumps, 10 horsepower, 5 horsepower sewage pumps, and a 1,000-gallon collection tank, much smaller than what you folks have here. Large vacuum stations, 800 connections to 1,500, might have 4 25 horsepower vacuum pumps and 2 30 horsepower sewage pumps and 5,000 to 6,500 gallon collection tanks. Here's some examples of stations that have been done around the country. The main thing is house the equipment from the weather. Some engineers and municipalities choose to make the decor of the building to blend into the environment. The one up to the left looks like a typical home. Yours here at Oak Island look like nice beach homes. They're all typically have an emergency standby generator for extended power outages. And usually they have a biomass for the exhaust off the vacuum pumps. It's the only place that you have an opportunity for odors in a vacuum system, is the exhaust from those vacuum pumps. All of our skids are assembled, painted, and tested at our factory prior to shipping to the site. And then they're brought on lowboy trailers, and you have to have a crane on site to lift them into the building. Construction advantages of a vacuum system. Once again, shallow burial depths, smaller diameter pipe, smaller installation equipment, less excavation, minimized dewatering, minimized disruption to existing utilities, reduced restoration, you don't have any manholes, and the ease of making field changes out there in the field. Operational advantages, we have a sealed system, so we should eliminate any infiltration and inflow. No exposure to raw sewage or dangerous gases for your operations people. No exfiltration of wastewater into the environment to pollute your canals, waterways, ruin your shellfish and fishing. That's why we were here in the first place. It's a constant system monitoring. Your system's under a test from day one. Should there be a problem, your operations people are going to know it, have to identify it, take care of it. Once again, shallow burial of the pipe shouldn't be a big deal. There's no line blockages or grease buildup in a vacuum system. With those velocities, your scouring velocities within that piping system keeps any line blockage or grease issues to a minimum. Odor and corrosion is minimized. We do use stainless steel holding brackets inside those buffer tanks. That's the only place that you'd have any opportunity for corrosion. The odor is minimized. The only place we have odors is the discharge of the vacuum pumps, the air off of the vacuum pumps. And no power required at the valve pit. The only place we have power is at the collection stations themselves. Services that AirVac provides, we believe in a team approach. As we did with you folks at Oak Island, we went in and did preliminary system layouts, saw how many it was going to take to do the island, did preliminary engineering plan and cost analysis, capital costs as well as long-term O&M costs. We'll assist with your design engineer with detailed design as much as they'll let us. We can provide construction field services as we did. We can be there for assist with the home hookup and valve installations. System startup. We do operate a number of systems in the country that don't have operations people to do it themselves. And we offer operator training and help with the local plumbers or any of that to give them a little presentation on the few idiosyncrasies that are different from gravity sewers and to the vacuum system. And that fat guy in the bottom right lost about 50 pounds, and I hope I look a little skinnier. Our website provides a lot of the literature and some of the other things. If anybody would like to access that, feel free. That does it for my hopefully quick explanation of how the system works and what we provided here at Oak Island. Now, I've also got Denny Moss, head of our engineering staff, that's worked real close with Black & Veatch throughout the design process. And I guess now, Madam Mayor, we can open it up to questions and answers?
David, do you have some information that you can give us, just to know, we'll take a break at 3 o'clock, so do you have any information you can give us as far as just a quick overview of issues that you might see coming up in the future? How well the system's currently running, what you think we need to do to get it to run?
I don't know if Jenny wanted to go ahead and say anything now or not. The system itself is working ideally. We have had a few problems in the beginning.
Okay. Thanks.
Okay, now start.
All right, the system is working. We have had a few problems, just like everybody else has, is mechanical, and things do happen. We had a few spills, we had a few blockages in a few people's houses that occurred, and we have worked on a few things with AirVac to find out and put things in certain places to help with those problems. As they keep talking about, it's an air-induced system. The problems we had last year on the West Beach, we didn't have enough air in the system to be able to pull all the liquid and solids to the facilities. We made a correction in October with their help. We put in a EAAC, air-inducing unit, and that'll keep the air, hopefully, on the unit so we can keep those lines cleaned out. The thing that we are seeing, is the reason why we're here basically, is we've got to decide to figure out how we're going to handle new construction or larger homes. And that's the thing we do have to look at. We have been able to go back and take some water readings on the beachfront where we have electronic readings. We started pulling some water meter readings, and you can tell when they get off the beach. And that's our problem. Everybody here comes to the beach and everybody leaves the beach about the same time and goes take showers, do whatever they got to do to go out to eat for the night. All the renters, they're going to the restaurants. So they're all taking showers at the same time trying to get the restaurants before they close at 8 o'clock. So that's what we're seeing our big flow. And what they talked about earlier, you figure out the flow in the mornings and the evenings. And that is what we're seeing. What we've got to determine is how we're going to handle these things when they come to us. In the areas, on the wooded areas, we do have a single pit with 4 connections. On the beachfront, first row is 2 houses per pit. We have larger lines closer to the vac stations, and we have larger lines on the beachfront, just the way the town was laid out. We can make more adjustments where the larger lines are than what we can where the smaller lines are. The smaller lines won't allow us to do much growth at the end. But that's not to say that we can't do growth. If we want to add things, we can add things. And we can add it and tie it into an area that can accommodate it. A person may have to lay a line down the road so many feet and tie into a 6-inch line instead of tying into the 4-inch line in front of them. That's something we can look at for growth. But the system itself operates the way it was designed, and it is running currently the way it's supposed to. We had a state inspection last year, was our first one. We passed it. We had a few things they wanted us to pick up on paperwork, and we made those adjustments. As far as the large structures, I don't have a magic number for bedrooms. I don't really care about bedrooms. I care about bathrooms.
Thank you.
I care about fixtures. I care about those kind of things. To me, if it's a room, it can be slept in. And if it can be slept in, it's going to have a person in it sleeping, and that person's going to take a bath. So just because it says 4 bedrooms doesn't mean that's 4 bedrooms of people. That could be 20 people in that 4-bedroom house. Another thing we got to look at is the rental units. I mean, we need them, but when somebody comes in and rents a house and has a wedding or something at it, I have 1 buffer tank or 1 pit for them, and they're bringing in 100 people for a wedding. That's what I have. There was a wedding this past weekend. We didn't see any problems with the system with what happened or occurred, and we did have a large volume of water that they did use. So the system is working, and that was always on the very end down at Kings Lane. Yes, sir.
David, two problems you might want to speak to is the smell and the heating in the pump stations. Could you talk about those for a minute?
We've looked at we have a heating issue. We've had some of the council members come do a sort of a spring tour. We didn't give them the hot summer tour. We gave them a spring tour. The heating issue is something that we have had, and we've tried to correct it on some small measures. We put in some air conditioners for the electrical components, and we put in some water coolers for the oil lines to try to cool the pumps down. It is a concern, and we have had two different engineers look at it, Black and Veatch being one of them, and then an independent person out of Wilmington. All air vac stations are not air conditioned. We need to look at either trying to improve on our ventilation system or look at some way to cool the units off. This year, with the budget restraints that we have, we're going to put chain link fences or gates where the big doors are. So this year, when you ride by, you're going to see the doors will be open, but they'll be secure with chain link gates. So nobody will be able to get in them. But it's going to help us on our heating problem because we can't afford right now to put air conditioners in. The odor.
One thing I might want to mention, though, you might want to mention the fact that next year that we're going to be getting some capital replacement cost money in the budget that we might be able to.
But last year we hired a company out of Charlotte who came in and looked at our rates and our schedules and our fees and things like that. And they gave us a progression program to start building up a capital reserve fund to start to have replacement cost and replacement money to replace certain pieces of equipment as the age of the system goes on. This current year, I think we had like $52,000. 58. Next year we're in the 70s, and then the next year we're 500 and some thousand.
30
or
60. 60, 560, I think.
560. It's a number.
Then the next 2 years it gets on up to $1 million after the 5th year.
But we're going to grow that, and we will be able to do different things within the system. And so the reason why we're pushing the air conditioning back or changing the ventilation isn't that we don't want to do it right now. It's just that I don't have the funds, and I don't think y'all can take too many more rate increases. And that's what we're trying to do, avoid. So right now we're doing different things to help with the heating issues. But when you ride by, you will see the doors open. You are going to hear some sound. If it gets to be too big an inconvenience to us, call us, and we'll try to do something else. The odor that comes out of that, it's a crushed coconut product. It's a carbon product. We had the first year we had it, we let it sit too long and try to run too long. We tried to get 1.5 years out of it, and really the only kind of life we're going to get out of that is really about 12 months. So this year we've already changed them. At Middleton Lift Station, that's a total different odor. That is not the vac station odor. That is the raw sewage there in Middleton Lift Station that you smell. Because that's the lift station that leaves the island. So that's a different beast, I should say. We're looking at doing different kind of odor controls there currently. We're getting ready to add a different chemical. It's starting to smell like grape bubble gum, hopefully by the next week.
No, wait, if we get through all this, then we'll take questions. Okay, we'll hold the questions until after you get through, because I have a lot of questions about why with the air handling and the odor and stuff, so.
That's a short overview to 3 o'clock.
We will take a 10-minute break, and then we'll come back and let the council go through all of their notes and questions.